Hey everybody, this is Larry. This is I always have to check day 27 of the 30-day Leetcode challenge. Hit the like button, hit the subscribe button, and also hit the refresh button. And there we go, Maximal Square. Okay. Uh, Maximal Square. Given 2D binary matrix filled with zeros and ones, find the largest square containing only ones and return its area. So I already have a video on this, which I think I did a little bit of an explanation about, but still, so the short answer is I have done this problem, so it will make live solving this easier. Um, and and it's not because I first solved this problem more than a decade ago, and it left such an impression on me as an example of dynamic programming and kind of a cool way, or I don't know, for me, I thought it was cool at the time, that that I still remember to this day. So it's not like I solved this recently, but I'm gonna solve it for y'all, and then I'm gonna go over why that logic works, and go over some examples. Um, cool, let's go. Uh, so now and right now I'm just thinking a little bit about, like, actually, should I code it first? Okay, let me just do the explanation first so that you have something to make sense to follow along. But the idea is that given I'm doing ASCII art, you know, the most beautiful ASCII art, hopefully. So you have something like this, right? And the dynamic recurrence starts with, well, what's the max number, or what is the max square size that ends at this index, right? And that's one. Okay, there's a zero, and yeah, and so forth. And that's kind of the recurrence we want to get on. Um, and the kind of yeah, and the way that we want to think about it is the max size that we have here is um, is a you could can we represent that question in terms of itself, like, recursively, and in a way that leans toward you know uh, a better answer. And usually I would solve this bottoms up, but I'm going to try to maybe mix it up a little bit. Uh, but yeah, but the idea is that, okay, now you fill this one, and so the best answer here is one. Here it's still one, and so forth. But once you're here, well, let's look at what we can do, right? We look at this the three directions. One is here, that's one. There's one, and this is one, right? So what does that mean? That means now you can construct a square of size 2 from that. And how does that come about? Well, so now, and maybe I'll do another illustration here. So then now this means that this is a 2, right? And similarly, this one here, you could see that the biggest square we can make here is 2. This is 1, this is 1, this is 1. So together, this will allow us to make a square of size 2. And how does this work? I'm going to illustrate in a short while um, with a big example, because I think 2 doesn't really show you enough. But yeah, going down, similar, and then here, this is 2 for that reason. And then now looking at those 2's, this is a 3, right? So that's kind of our dynamic programming approach, is by looking at the left, the up, the vertically up, and the diagonal upper left, and then get the min of those 3 numbers plus 1. Now that seems way magical, and I understand. And let's figure out why it works, right? So what does this matrix mean? And here, what does this 2 mean? This means that there is a square of size 2. And this 1 means there's a square of size 1 that ends with that number as the bottom right corner. So if you want to draw this out a little bit, I'm going to use dots and hashtags on a 2. So now this is something like that, I think. So this is this refers to this square, which is on row 3, column 4. Let's use zero based. And then now similarly, what does this 2 stand for, right? This 2 stands for something similar, but to the right of that. Um, and then now let's look at what this one stands for. The what's it? X is oh, I got that well. Oops, sorry, friends. And then y is equal to 3. So also similar. Copy and paste. So similar that I can copy and paste. Right? So now we have these 3 triangles, right? Or sorry, these 3 rectangles, right? Um, well, if you draw them overlapping each other, and really need to set up one of those MS Paint things, um, is that when you draw them on top of each other, you get something like this, right? Let me put it in a separate thing. So that's how it looks like overlapping, right? And from that, well, now it's clear why this, or a little bit clear. I mean, it's not easy to come up with, but we begin with the proof, and then we could try to think about strategies on how to come up with this if you were to face problems like this. And then yeah, so now, this is the overlapping. If you put all these 3 things together, um, then here, what does it look like, right? Well, as long as this is at least, or if this is filled in, then you can fill that in to fill a square of size 3, right? So that's kind of the idea behind it, and you can play around with like different overlapping. Let's say for this square, this the answer is, let's say we remove this, so then this answer is 1. So then here you actually, your most best square looks like this. And what does that change, right? So then now your overlapping square looks something like this. Maybe did I change the wrong one? No, I mean, yeah, no, that's so your no, well, yeah, so something like this, right? And from that, because at this point, your biggest square is 1, your biggest square is 2 at here, and your biggest square is 2. But because of this, you know that this is not filled in, so this can only make a square of size 2, if assuming that this is already filled in. So that's kind of the logic. I I think it's easier if you draw it out yourself using pen and paper, old-fashioned pen and paper. And if I had one of those clear, clever whiteboard apps, that's maybe what I would have done. But that's the algorithm that I'm going to do. And then once you kind of illustrate this and ask the right question in terms of dynamic programming um, then it becomes easy to code, and I will code in front of you for live. But yeah, and the question, quote unquote, here, or in dynamic programming terms, this is the problem in which we try to find a subproblem. And the problem we're asking is, what is the biggest square that ends in this square? Or by ending in this square, I mean having the bottom right square as that square. Okay, cool. So now that we can just call a DP array. Let's just set the default is equal to 0. Actually, let's just call rows is equal to the length of the matrix. Columns is equal to the length of the first row. It's not always going to be, in this case, it is a rectangular matrix, so that's why it works. And then now we can set it up. This is very Python-y, don't worry. It's just a matrix of zeros from rows to columns, of rows times columns. And then now we can yeah, now we can do it, do a loop for it. Yeah, I think this. I'm just trying to think about how to handle the base cases. So sometimes, depending on how you want to do it, and this is just an implementation detail that I'm giving a little bit tip about. You could do it some. You could do it with if statements and just like checking for bounds. And you can also do it by changing the boundaries of your of your dynamic programming cache, if you will, or the array that just the matrix that you're setting up, and and um, and yeah, and have to implicit base case that way. I'm gonna actually change this for that reason, and then um, we're also gonna play around with some stuff, which we'll talk about in a little bit. Um, so now we can do for x, x in rows, for y in range columns, and that's actually just for query. Let's go from 1 to rows and 1 to columns 1. This is exclusive on the right side, so that's why it's +1. And then now we can just do a symbol of, okay, well, if the with matrix of x and y, well, in this case -1 because we added 1 to it, is equal to 1. Is it a number 1 or is it a string 1? Sometimes it's not clear. Yeah, see, it's a string 1, right? So, okay. But that's just like a Leetcode specific thing. I mean, I think in an interview, it probably doesn't matter that much. Like, you talk to the interviewer, it takes half a second. But yeah, if this is the case, then dp of xy is equal to the min of dp x minus 1 y, dp x minus 1 y minus 1, and then dp x y minus 1 plus 1. Yep. And then that's all you have to do. Now we want to get the best, because your best result can end in any, I mean, in this case, actually, it's at the absolute lower right corner, but you can imagine there's another column with zeros. And in that case, your best square can end anywhere. So you have to check it every time. I like to be liberal with these, so I'm going to put it out and write best is equal to max best, and then here you go. And that's, I believe that's maybe right, unless there's like typos. Oh, of course. So yeah, so I actually knew this while I was reading it, but we have to return its area, where the thing that we're tracking is the width of the width of the square. So we just have to times best to get the area. Actually did realize this one, but forgot about it. That's why we test. And let's do some basic, let's just do a small thing. Just some small examples. It is as annoying to watch as it is for me to type, but that's annoying things will always be part of software engineering. So hope you appreciate that. Okay, that just means I typed it incorrectly, I think. Oh, yeah, I lost the quote. Yeah, okay, so that looks okay. Maybe I want to do one more with 3, because just to kind of check our previous one, which yeah, looks like some just for a little bit more than just base cases, and a little bit bigger. Okay, so that looks good. Let's submit. Ooh, no. Oh, okay, well, okay, fine. I actually thought about checking this one, but I wasn't sure that like for n is equal to 0, it I mean, I don't know. You could definitely, because I feel like they don't give you the constraint for this problem, but usually I think the more recent Leetcode problems, they actually been better about it by giving the constraints, and also they don't try to catch you with tricks like this anymore. But I could be wrong. Anyway, not a big deal, obviously, because here we're just trying to figure out the algorithm and not necessarily edge cases. Well, I mean, edge cases are a big part of algorithms, but Cool. Yeah. So we got this right, and there you go. An n square algorithm. So yeah, analyzing this is well, let's say rows is n, or let's just say this is O of rows times columns, or n times m, depending, or m times n, depending on how you want to name these n and m's. I've been trying to be better about using them as rows and columns, or r's and c's, so that it's more clear which one is row, which one is column. But that's the convention I've been using. So yeah, so that's maximal square. As you can see, because we do two for loops, each of them does like a all of one operation. So this complexity is going to be O of n times m, or m times n, or row times columns, and the space complexity is also going to be rows times columns. And yeah, and so the next question, as a little bit of a upsolving or stretch goal or whatever. Well, first of all, is if you struggle with dynamic programming, and especially bottoms up, which I had for a long time, like I was always better with top down. Well, I'm going to put a link below for yesterday's video. So in yesterday's video, I went on the longest common subsequence. I went through the entire process because it's a very common problem. So for that problem, I went to the top down, then went to the bottoms up, and then I showed how to shave a memory trick to shave a dimension of the space complexity, and to that end, as a way to try to figure out myself, or trying to learn myself and more practice, I'm going to also show that here. So now, as we talked about, this is of rows times columns, or n times n times m, or m times n. That's a mouthful. But let's get this complexity down a little bit, right? Can we get it down to O of n space, similar to what we had yesterday? And the answer is, well, one, watch yesterday's video, and if you do, then you'll find that I can do this actually pretty straightforwardly. And I'm going to show it to you, and I'll explain a little bit, but definitely, definitely recommend it. Well, recommend y'all checking that one out. So now I type this out. So now we just have two arrays initialization, and we could even just do proof is equal to dp x minus 1, and then now is equal to dpx. And then now it's as simple as, well, get rid of this because we don't need that anymore. We don't need you anymore. And now we can just copy and paste. Proof for previous, you can just copy and paste, just like this, right? And the only thing that you have to add is that when you're done with a row, when you're done with a row, you have to reset the variables, or your now is your next now, or your next previous will be now. Does that make sense? Basically, you're shifting things backwards. I do a better explanation about this yesterday. So again, check out the links on the comments and description. And yeah, if you have any confusion, definitely leave a question or leave a comment, and we'll get to it. Cool. And yeah, and now for y in range from pose plus 1. So now previous y is equal to now of y, and then now of y is equal to 0 to reset, right? Now let's run the code real quick, because just in case for typos and silliness. Looks okay-ish. So let's submit it again, and there you go. And that was really easy to remove one dimension of space, right? So that's why I always try to allocate. Once you learn it, it's really easy. It cannot be applied for every dynamic program problem, but when it can, it looks great. And now I'm going to show you a little bit about the performance difference, as I did yesterday, just to kind of give you a sense of, give a sense of like what the memory difference is and stuff like that. Second. Okay, so it turns out that there's not that much difference. So uh, for this problem, but as you can see, because I think the inputs are just too small, which is fine. But as you can see, this is a very easy thing. So and it is a technique that comes up a lot. So definitely recommend it. And now the complexity would be O of n times m or rows times columns, and the space complexity, as you can see, is just columns, right? And then the next question you may ask is, well, what if rows, like what if it's a thin, or thin or long, what if this is a long matrix, right? So that you have like say 1 by x. So then now it's going to be x anyway. So you almost have linear. Well, in this case, you know, just flip the matrix. That's my answer to you. Or I mean, you could also do some math to do a swap, but essentially flip the matrix from rows to columns or something like that to take the lowest one, and then that will improve your memory efficiency. And that's all I have for this problem. Let me know what you think. Let me know how you did with this problem. Uh, this is really hard to come up with if you haven't seen before, but it is a grid related thing that just it to be honest is a little ad hocy. I mean, it uses dynamic programming obviously, but it's a little ad hocy, and I don't know if there are similar problems, but not really. Like all of them has like this one little observation that you have to make on the problem, so it's a little tricky. But once you do uh, one way or another figure out the algorithm, um, practice with the dynamic programming coding because definitely there are a lot of ways to go wrong with programming and dynamic programming coding. Like you have an off by one sum and everything is wrong. So yeah. Anyway, let me know how you think, how you feel, how did you do? Hit the like button, hit the subscribe button, and check out yesterday's video. I go into more depth about dynamic programming and breaking it down. And I'll see you tomorrow. Bye bye.